1 and roughly lectures 3 through about 16 include new things, and that's today I want to talk a little bit about, first of all, this function that lies between the Lagrangian and the Hamiltonian and what those two things look like when we treat them in Unit 2. But this particular unit has a Chapter 12, which you're welcome to turn to and begin learning some of the stuff that we'll show today. But I also want to introduce what I think is really important for modern physics, or modern classical mechanics for that matter, and that is the use of symmetry operators. We're already doing it right here. And in fact, these two objects, the matrix that bounces from the floor and the ceiling bang, the thing that bounces the system off the ceiling, are in fact Pauli spinor matrices. The famous sigma z, which is up at the top of this chart that we have here that we'll be using later on in Unit 4 and beyond. The operators of sigma z, which is at the top, we call it sigma a, or if it has a 1/2 on it, it's a spin operator, SA. And then the next one is called by Pauli sigma x, we call it sigma b for balanced. And finally, the imaginary one, sigma y, is what it is in Pauli's language, but we call it sigma or SC for curly, complex, Coriolis, centrifugal, a whole bunch of things that begin with C, chiral being the most important. It's the one that has chirality to it. Well, we won't be using any but the A and the B operators. We don't have any complex numbers in this particular theory, but I emphasize that this method of doing mechanics by matrices is a really neat way to get used to the quantum mechanics, which, as you know, has almost always, since Heisenberg and Jordan, used matrices in the theory. So we're going to jump ahead to where we stopped last time in this lecture 3. That is right at the end of the discussion of using matrices to do bouncings like the picture here, where there are a lot of bounces. This is the case that has a mass ratio pretty high, 49. If we were to plot that 49 on our graph here, the thickness of the chalk would be too much to make it a useful diagram. We talked about a ratio of 3, 4, 3 was an interesting one, we'll come back to that one. 7 was the super ball pen ratio that we carried through a few bounces here on the board. And then here's 16, and now we want to talk about 49 would be somewhere right in here between 16 and infinity. You see, it gets kind of crowded. So the idea is to undo that crowding by rescaling this diagram so the ellipse becomes a circle. And that will be what we talk about here. But of course this ellipse is a ratio square root of 49, which is roughly 7. And that's what we're doing here. So I'm going to go quickly through how we derive the matrix from the equation for inelastic balance. That's where all of this comes from. we're talking only about elastic collisions using these particular matrices. You could actually put damping into these things. I'm not going to discuss that in this chapter. We're doing sort of the pure stuff, right? Not the dirty stuff. But there's room for dirt too in this theory. Okay, now the matrix that does the rotation that we're talking about here is a product of reflections. And we'll do a little bit of reflecting on reflections and talking about two mirrors, literally. And all of those three matrices there are reflections in a sense. In fact, I will state that if you look at them correctly, they are all three of them reflections in 3 dimensions. But a mirror like you see pictured here, where I can change the angle between the mirrors, is used to be well known to people that went into clothing stores. It was usually found in men's clothing stores and not in women's. I don't know why that is, but the idea is that you get to look at your image not in the reversed form, but if you look in the right place, you'll see your image where everything is exactly, the right hand moves to the right hand. So we have to get used to the idea of being able to rotate using this thing. And what happens is, if somebody is standing in front of the mirror and they rotate one of the doors, that image will rotate twice as fast or twice as many degrees as you change the thing. So you can literally use the mirror to look at your backside. And I guess that was an important thing back in the old days when you had really fancy stuff on your clothes behind, a little ribbon or a little band or something like that. I didn't know. Anyway, men's clothing stores used to have these things, and some of the old ones still do. Anyway, you've heard the expression, it's all done with mirrors. Group theory, that is absolutely right. Everything in group theory starts with mirrors. Mirror reflection, namely this, is the most primitive operation. It's the one that can be done in 1 dimension. You have a line, right? Okay, you put a mirror, you just make a mark, and you imagine there's a mirror that takes everything on this side and puts it equally on this side. And then everything that's over here, presumably the mirror is double-sided, takes that and puts it over here. Now what's cool is, if you take 2 mirrors and do this one first and then this one, then you'll get a translation of that line. So translations, which you think is just sliding along, right? It's 2 reflections. And as you close the mirrors together, the translation gets small. Again, a factor of 2. You get bigger. The translation is growing too at double the rate. Okay? And then, as you go into 2 dimensions, as you tip them, you see, you're doing a rotation by twice the dihedral angle. And that's what I want you to get into your heads. How does that work? Because that's the way you understand spinors and spin a half in quantum mechanics. But you might as well learn it where it's really useful here before we do any quantum mechanics at all. We'll have a lot of classical quantum analogies in this course, and a lot of them stem from precisely this geometry. So it makes it very important. Okay. Now, as I say, this is really a hard thing to draw geometrically. I used to force you to do it. Now the problem I'm giving you today, you can use circles. We'll be modern and take some of the work out. So basically what we're doing is we're multiplying each of our velocities that we've been using to make our kinetic energy sum of 1/2 m1 v1 squared plus 1/2 m2 V2 squared. We're going to write that thing in terms of big V1 and big V2, uppercase V1 and uppercase V2, who are simply scale products, rescaling of the velocity space by different numbers. And I just see here another typo, one of those cut and paste things where you forget to change it after you've done it. This obviously has to be 2. So we're scaling by the square root of the mass associated with the first or the second dimension. And when you do that here, and this is the result, you get a matrix that, this matrix right here, it can be changed so that it's simply a transformation of the uppercase V. So I go through here, and that means I have to multiply this thing by a square root of m if I were to just have it V1 here. And then I have here to divide, that has to divide by that m, so they cancel, there will be no factor there, but I will get a square root of m2 coming in on that one. So I end up with here a square root of m2, because m2 is being divided by m2 there, and then a square root of m1, because I had an m1 already, and another square root. I was dividing by that, and I multiplied by square root of m on the, there's a divider, there was the multiplier right there. So this is the matrix that describes rotation in this expanded space that is going to consist of a circle. So the cool thing now is that in fact this quantity right here on the diagonal, as well as here, is the same. And of course, what we did by doing this transformation is turn an ellipse in little v1, v2 space into a circle in the big V1, V2. So in big V1, V2, the ellipse has blown up to a circle. Now we're picking M2 here to be 1, say, and that's going to be the easiest way to do all of this algebra. So just set M2 equal to 1, and only the ratio between these masses makes an essential difference in the character of the trajectory paths. So that's a saving in algebra as well as in geometry. If M2 is 1, the square root of M2, which should be right here, would just be 1. These two coordinates are the same. So you can see here that I haven't done anything to the dimension that was the long dimension. I've simply expanded by the square root of 49, it's a factor of 7, this particular coordinate, so that it's equal to this one.
Dr. Harter, so in this case even the center of mass velocity would get rescaled, right?
Yes, all of the things that are in here,
Yeah.
like the V1 equal V2 line, which was 45 degrees before,
Yeah.
now it's here. It's got a slope of square root of M2 over M1, which is just 1 over the square root of M1 for us. It's square root of square root of 1/49th, 1/7. Right? And its reflection down here, right? When we did the collision, right? Off the floor, which is right from here over to here, right? We ended up at 45 degrees as well.
So when we rescale the velocities, the magnitude of the center of mass velocity changes because of the scaling, but still the slope should still be 45 degree, right? Like I can draw the circle, and then V1 is my x-axis and V2 is my y-axis, so I could still draw a 45 degree line from the center of the circle, and wherever that intersects that circle should give me the magnitude of the center of mass velocity.
What's going to happen is there's going to be a momentum line. Here the slope of the momentum and this tangent slope here is 49, right? Because that's our mass ratio, right? So the thing that's, the slopes that are being bisected in all of the collisions, right? If I get down to, someplace here, then I draw a line to do a collision with slope 49, and there's where it would end up if it was inelastic, right? But we draw a compass that comes around to that point. Remember? It's just a little hard to see here. Well, that's going to be this thing. Here is the line, these things right here, okay? These things will have a slope of the square root of the mass ratio, or just 1 over, I should say, exactly equal to the square root, with a minus sign, of 49. So the slope of this right here is 7. So the line which had a slope 7 over here, right, would in a Lagrangian plot have reduced somewhat, square root of 7, right? But the 49er that was going through here, it's now going to be square root of 49, which is the same as the slope of this line. So, just a coincidence that we have here this line now, which used to be the square root of m1 over m, used to be m1 over m2, is now the square root of m1 over m2 in slope. It will be bisected by this, and will be at right angles to it. This is really cool. First of all, I can do this with a compass. I don't have to draw an ellipse,
Okay.
which is done by compass, but it's many steps. One shot, okay? And then everything that happens here is really very simple. And in fact, all you do is figure out how much you rotate with one of these, and then you take your compass and just keep marking. Every collision is just a mark around the thing until somebody hits a floor or a ceiling. As long as we're doing a ceiling and then off the ceiling, you see, floor bounce, and then collision, C, and then off the ceilings, we're talking about the product of the ceiling matrix, uppercase C, and we're talking about the collision matrix M. M does this, and then ceiling does that, and then M does that, then ceiling does that, and so forth. Together, those two matrices in product, CM, is a clockwise rotation that we had in the previous slide where we made a picture like that. So let me go ahead and put that on this slide over here. See if we've got so each of those CM products, call it R for rotation, is a clockwise rotation, and rescale is a very legitimate clockwise rotation in the rescaled space. It literally is a rotation by, well, you got to figure out what the sides of the triangle are and then take the arc tangent. So I've already got a cosine of theta equal to m1 minus m2. That's this component right here, m1 minus m2 over m1 plus m2. You see that, right? In this matrix is the cosine theta right here. Then this thing right here, 2m1, m2, okay, divided by sum of mass, m1 plus m2. That's sine. Now you check to make sure that those two add up to 1, and they do. Just a binomial, okay? So, what we're talking about is the arc tangent here of 14 over 48. That's 68 degrees, roughly. Okay? So that's this angle right here. And then half that angle is very interesting. It's right there. So that figures in the problem I've given you. It's a chance to see both geometry and algebra solving a problem. And it's a matter of taste, which one is easier. I think geometry wins in this one, but not by much. Okay, now we're going to play with this one because it's almost periodic. If you run this one, it looks like it goes over here, comes back, and repeats, but with an annoying difference. Do you want to go ahead and try it? This is what he I think has set up here, that, and we'll just go ahead and let it run at a slow speed so that you can see it go. There's it. There it goes. And now we're going to do the bounce around the circle. Here it comes back and hit the big ball.
Another C-line to form a pair.
Hits it again. Hits it again. Hits it again. And now it gets over to the other side. Now it's a question of who hits who and whether you hit the floor first or they have a collision first, which is what they had there. But now we're back over and we're in a slightly different place. Looks like it's going to be periodic, but not quite. Not quite. It's sort of little double lines there. And you see it couldn't have been because there's a little deviation here from this thing right here and that one. This isn't quite, this thing isn't quite meeting on that particular line. So what I'm asking you to do in this problem, and let's just, I'm going to go ahead and bring that problem up right here. And explain what it is that we do. I'm going to say, suppose I didn't know how to solve this thing geometrically or algebraically. We're reverse engineering this thing. We want to find a mass ratio slightly different from 49 that makes this thing periodic exactly. It's right on. And that means, roughly speaking, that we wanted to make it so that the angle that this turned is a nice integer divisor or multiple of pi over, well, basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, pi over 11. So that I really do have it go out and then come right back to where it started. And therefore be perfectly periodic. Now, this is, you think, sort of a game? It is. Physics is a game. But it turns out that classical systems that have a perfect classical periodicity will have extraordinary quantum behavior. So that's the kind of thing we look for. We look for situations where the classical model is itself a perfectly periodic, a Poincare recurring system. Poincare is the one that really realized that classical mechanics had to lead into quantum mechanics, but had to do it through understanding oscillation, and it had to do with having resonances that were perfect. And so what I'm saying here is if trial and error shows that 48.37 has very nearly periodic paths, and go ahead, if you would go ahead and put 40 or the number 4.837 in there. Actually, I think you could do that. You have a limiting of 4 digits, so you can't go any further than that.
This tends to fight you a little bit. Sometimes you have to poke it in several times. 837.
Yeah, instead of 4.9, 837. Did you get that much in there?
Yeah.
Okay, let's run that.
And then look up here to make sure it really held, that it really entered properly, and it is.
Yeah, I see it entered up there, yeah. So if this isn't quite the same as this one had a little smaller scale, but be that as it may, it should go over there and really return, except for the fact that it's going to return on the bottom and then on the top. It actually takes 2 full revolutions to go through. But to the error of the pixels, I think that this one is okay. But what I want you to do is calculate the exact answer. That's going to be your job. I'm going to ask you to calculate a formula for what that mass ratio should be so that I get 48.37 ... It's an irrational number. In quantum physics now we do things to 18 figures sometimes. So you would have to know this to 18 figures in order for it to work and be right in modern accuracy. But at least 3 more figures will be acceptable. But once you figured out the formula, you can get it as much as you want, as much precision as you want. So there are 2 cases here. Now this case right here is the easy one. The one that doesn't go chaotic, and that's the thing I ask you about, is how strongly affected by the size of the ceiling is this? That's where the periodicity can get hurt. But this one seems to be completely immune. And this one is the one where we simply set the initial velocity of the number 2 mass to 0 and have the number 1 mass come up with a positive 1 velocity as though it had bounced off the floor, but the number 2 is not moving.
We could do that with the control panel.
Right.
And that's just entered. We got a new set of initial conditions. The ceiling is still the same height.
Everything's the same, except for the initial velocity of number 2. Bang. And you see, the difference here will be that instead of starting down here and having a collision to go up and eventually come up, ending up that high, just as high as you started, almost, in case of not getting it perfect, that initial point is right on the axis.
And here the cursor is. You can see it started here. I can restart it so you set it in your mind. Bam.
Bang, yeah, there you go. And then the thing has to go off the top, go back to the circle, hit again, bang, bang, bang. And if everything is working, and this is what's really cool, is right now it really matters whether that thing has enough speed to go and hit that thing before it gets to the floor and stop. So now we're for sure starting with the same initial conditions, except we've had this big path, right? And now it should cover that path perfectly, if in fact that number was correct. But 48.37 is not quite correct. So if you run this for a long time, you'll see that it starts to slide off and eventually fill the whole circle.
Just let it run.
You see? That's called ergodicity. Most of the initial conditions are ergodic. That means They cover all the space they have, the energy momentum allows. This system, with the exact number, whatever, will not. It will be Poincare recurrent, non-ergodic. Very important piece of dynamical knowledge that you have. See, it's doing it again. But you can see that the number wasn't quite 0. And so if you get the right number in, or to the extent that you get the right number in there, it should be 0 to that precision, you see, if you started at 0. Okay, so this is a beautiful example of something that is of importance for all kinds of physics and engineering, classical and quantum. Okay, now we're going to look at some that have a little smaller ratios and don't bounce as much as this. But this certainly gets us started on the geometry of multiple collisions and the idea of the Lagrangian and Strontian, which I want to emphasize now. Right now it's V2 has a velocity of 0.004. Okay, so it's not being perfectly periodic, but pretty good. It's good enough for government work at this point, right? So I encourage you to play with this thing on the numerical simulations. Just put in the numbers and see what it does. The one thing that helps if you you should notice that you can slow the time down. You can make it really slow by changing the speed there. That's too much, and now it's really done. You can look at your energy. If your energy isn't the same as what it was total before, which is 2.4 something, so you will make the numerical integrator fail by doing that. It will not be precise. So you can slow the thing down to make it more precise in cases where you are trying really huge ratios where it's doing this. If it's doing that, you probably ought to slow it down. But check your energy. If the energy E is not maintaining itself, whatever it was when it first bounced, you can't trust this numerical solution.
You sliced your time coordinate too coarsely.
Yeah. And this thing doesn't have adaptive step size. This one doesn't. We don't have an adaptive step size on this one, so it doesn't correct itself when it's going too fast. Okay. Now the other problem that I'm asking you to do here, we'll talk more about that probably in the next lecture, but I think I can get through the essentials of that today. I want to talk about the group theory of these operators. In particular, whenever you have a situation that is repetitive like this, a symmetry is hiding there. And the symmetry in this case is the fact that you have decided that the only evolution operators that you're going to accept are ones that belong to a finite group. In this case, the group is D11. I want you to look at D3 and D6 in this problem, where we have elastic M1 equal M2, 3-to-1 collisions. It turns out, unlike the 7-to-1 or 49-to-1, this is a trigonal or hexagonal, depending on how you look at it, symmetry.
So, Dr. Harter, this is a problem for which the upper ball will bounce to a height of 4 times the original height, right? If the mass ratio is 3:1.
Well, yes, this one, as it says, is the 3-to-1 ratio. And as we'll see, it is very periodic. a beautiful periodicity that has this symmetry. So we'll get to that in just a minute here, I hope. But before we do that, I want to go back to the this fellow who's not symmetric. You see it a little off, but needed some repair work. Now,
Excuse me.
oh yes.
Can you briefly describe what is a group? I'm not familiar with group.
Wait, I didn't hear that.
What is a group? I mean, I haven't been with group.
I'm going to
don't know
explain
what
that.
is-
I'll explain that. Yeah. And this is a time to learn that, because this is such a nice, simple example that we're good here. But I want you to notice that if you make the mass ratio a perfect square, then the triangle that you get here has an integer symmetry. In other words, this is like a 3, 4, 5 triangle. 14 squared plus 48 squared is 50 squared. It's one of the Pythagorean triangles. So that's another kind of symmetry. But the symmetry that you get for the shape doesn't show up in the diagram. It's real close, but D11 is a symmetry, which is, completely different from that. So this is the nature of mathematics being cruel. It's not. You might be, fooled into thinking, I've got that symmetry, therefore I should get it here too. No, but it is true on that next problem. Mother Nature, she's a bitch. Okay, so this is just a blow up of that so you can see a little bit of the geometry, and this half angle geometry is crucial for doing the solution. Reverse engineering this thing. See, usually we think of ourselves as being given the ratios of masses, right? And then something happens and we calculate that pretty well. But when your theory is good, you should be able to deconvolute it. You see, you should be able to say, what angle, I want a certain angle, what mass ratio will give me that? So that's what that first problem is solving that. And the second problem, of course, in order to get symmetries, you have to do that. Okay, let's go over this. The two archetypes of energy functions, which means in geometry, energy curve, or if I had 3 of them here, energy surface, or if I had 4 dimensions that I had to work with, energy hypersurface, okay? All of those fall into 2 main classes in the normal development of classical mechanics. If the energy function involves velocity, it's called a Lagrangian. That's what Lagrange. This is the French school of classical mechanics, Lagrange, and many people working with it. Meanwhile, across the channel and up the coast is the Irish school of mechanics, Hamilton. And Hamilton's energy functions are made not with velocity, but with m1 and m2 times v1 and v2. Momenta, P for impago, I guess. Galileo is the one that really thought of momentum first, but never quite developed it, not to the point that Newton did. But anyway, P is the letter we usually use for mv. And a geometrical procedure sort of analogous to the one over here exists for Hamiltonian too. The deal there is that the sum of the momentum P1 plus P2 will be constant. Now, when we said that momentum was constant over here, we meant we were on a line that had a slope, and I'll look at our very first collision here, SUV-VW, that line had a slope m2 over m1. But now we've rescaled the thing by not the square root of m, but the whole m1 and then m2. Okay? So what we've done by doing that is we've taken this thing that has a slope -7 and reduced it to slope -1. This constant momentum line is now sloped -1 to 1. Well, that's just telling you that the equation that is being obeyed here is P1 plus P2 equal a constant, which is a slope line like that, right? X plus y equal a constant. Is a 45 minus slope. Make sense? Okay? So every time we do a rescaling, all of the stuff that's in here is going to stretch. Okay? Now this particular rescaling, I've done two things. I've stretched this one and crushed this one by some amount. Well, how much? I'm talking about 4 squared, actually 16 here. Okay, that's the ratio I have here. So I'm rescaling both dimensions in order to get this. If I were to not rescale this one, the ellipse would cover all 3 of these boards, right? So I had to do some rescaling. But still, the connectivity here, the fact that this line here, this bisector that is 1-to-1 ratio in the Lagrangian picture, bisects the ratio that is m1 to m2 with a minus sign, in other words, a slope of -16. Yeah, that's still true, you see. The red line bisects this line of constant momentum. Well, now that line sinks down here, you see, from being 1-to-1 to now being a slope of m2 over m1, which is 1/16. So it went from 45 degrees to 1/16 slope, while this thing with its slope 16, -16 actually, went to 1-to-1 with a minus sign. Okay? So you can track all of the things that have happened in the mapping that takes us from a Lagrangian to the Hamiltonian. Now it's unfortunate that I don't know of any books that show this. But this should have been shown all the time. I bet you it's in the notes of Hamilton and Lagrange somewhere, and it's in a wastebasket and off in the ether someplace. But who knows? But geometry should be used. It's a roadmap through this forest of equations, which we're going to be building up in this class, and then in quantum mechanics that this is designed to help you with. So, that's the idea. Lagrangian, 1/2 m1 v1 squared, m2 v2 squared. Hamiltonian kinetic energy is p1 squared over m1 times 2. And the same with p2. Okay? All right. But then, the thing that we were just working with is halfway between these two. As we're crunching this thing down and extending this out, let's stop at the, well, I don't know whose school is it. Maybe it's a Spanish school, l'étranger. The stranger is Spanish, right? And this is where you have square root of m2 and square root of m1. You're half power way to this, and this is half power way to this, coming from the Lagrangian world that works with velocities. Now, just for the fun of it, I drew one of those circles that we use to bisect, or actually we don't bisect, we already have the center, then we just simply find out where's the final point if this was the initial, or vice versa. If this is the initial, then that's the final, time reversed. Well, that curve is not a circle, but they still bisect. So there's an ellipse here for this construction curve. And there's an even kinkier ellipse for the Hamiltonian.
So
But you
Dr.
might
Harter,
want to see that, but it's perfectly useless.
Dr. Harter,
Because who wants to construct that thing?
the
Right.
green circle is the Estrangian, is it? On
This
green
right
cir-
here,
Yeah.
we call this one the trunchion.
And what is the mathematical form of Estrangian? Like, does it have just as Hamiltonian is P1 squared or 2m?
Well, remember the whole motivation for this. That's a good question. You've forgotten the motivation. Okay, let's drop back here. Okay, what were we trying to do to this to make it into a circle?
Okay.
Right? That's your equation right there.
Okay, so the rescaled equation of Hamiltonian is your Estrangian.
And then it's the next one where I take the M1 and M2 and put them in the denominator. But here they don't show at all.
Right.
You see, that's what's so cool about the Lagrangian. The masses don't show at all. Now this is a very important game to play as you try to find analogs for quantum oscillators and electromagnetic oscillators and photon oscillators and the harmonic oscillator. Because the harmonic oscillator that we would most like to work with is simply x squared plus p squared. And I mean multidimensional x squared and multidimensional p squared. Forget the mass. There is no mass. Just some kind of spring constant is all there is. So when we make a two-state quantum system into an oscillator system, we're doing what Planck wants us to do. Regard everything in a cavity, electromagnetic behavior, as a relative. I mean, you didn't say this, but relativity and quantum mechanics are the same subject as it's what relativity is all about. That we're making these, trying to make these sales talks using the web to convince people that this is a very nice way, a quick way to teach it. We're really trying to get it so that quantum mechanics and relativity, which are the same subject, can be taught in a middle school. I mean, you can start doing it in a middle school. You certainly can do it in high school. You can do quantum field theory in high school if you carry this out. And that leaves you all that time to learn what's coming. Le deluge. You're in the middle of an explosion. The amount of stuff that's going to be discovered in the next 10 years, unless we get in a war or something, absolutely going to be mind-boggling. So the sooner you can start, the better. And that's what this is all really about. Preparing for the deluge.
It's the second week in November.
Yeah, we're giving a seminar November 14th.
Keep your calendar open for that.
2 weeks before Thanksgiving. Yeah, and hopefully you'll be thanking giving after you've seen it. Okay, now once you get these Estrangian, it's really easy to play the clothing store game. And unfortunately, this is a figure that I have lost. I made it some time ago, and then I've lost the original. So it's a little fuzzy, because it uses an old graphic technique. But the idea is fairly simple. It's this pair of mirrors, not exactly this particular. I think I broke the one that's in the picture here, but this is a replacement. And the idea is that you can see on the original object that's being reflected around and around and around here, a picture that shows a right-handed AB basis. Base is for singular for the two of them, or base as plural for each of these base vectors that are orthogonal, A and B. Okay, and you can see the reflection of that right here, and you'll see that it's not right-handed, and the writing's all backwards, you see here. But here it is back again, okay? So what we had to do was do a reflection of a reflection. This is a reflection by this mirror of this image. Then the second mirror right here, you see, is reflecting that image to this. And now it's back being a right-handed basis, but it's rotated. It's this one rotated by twice the angle. This right here, this angle is 60 degrees between the mirrors. There's one mirror right there, there's the other mirror right there, just like this picture's showing. Okay, so here's the original with its basis and then a little z-axis or c-axis sticking up out of the paper. Here I can draw it, there it's not there. It would be it's just sticking up in the same direction on all of these as well. And then there's a reflection of that, and so forth. You know, and then you do it an infinite number of times. You could really get inside this thing. You'd see all of these corridors going off in the directions of the axes of the hexagon. Which I think you can, you know, just something you really should play with to get a feeling for reflection operators in a non-trivial setting. So the rule is, if you want to rotate something by 120 degrees, set your mirrors to half of that. And you'll see a positive 120 degree rotation on one side, you'll see a negative 120 degree rotation on the other side. And between that you'll see reflections that are rotated also, but they're more than rotated. They've been flipped. They're not right-handed anymore. Now, the sort of an extreme case is the retroreflector. One of the things that the Apollo astronauts left on the moon on the first mission was a thing about yay big that consisted of right angles, a whole bunch of them, very fine mirrors set precisely as they could to 90 degrees. In other words, it was a very precise tail light of a car. If you go out with your little hand laser and shine however far you can see a car that's parked, so their tail reflectors are pointing at least so you can see them, and you shine the laser. I don't know how many people have you ever done this. You may not be able to even see the spot of the laser if they're very far away, but when your spot passes the tail light, it's all back in your face. You see a big flash. And that's because no matter what angle you come into a 90 degree, it comes right back out in the same direction. So the deal is that you can now go with a pretty powerful laser. Just a projector laser like one of these is not powerful enough to do it, because by the time it gets to the moon, this one isn't even working, so that would even work in this room. But the idea is that you can shine at the moon and it'll come back and you can record it on the thing. It's, 4 or 5 photons get back and you send octillion out. So the percentage is not great because 250 to 60,000 miles we're talking about, right? But that's the experiment that is talked about in science engineering many years ago, right after the Apollo mission. I just saw it on Mythbusters on Sunday. I think it was Sunday. And what the Mythbusters were doing was going around and doing experiments to counteract the one of the many myths, conspiracy theories, actually, that are present in the United States. And one of them is that the moon landing was faked. The whole thing was a fake.
Oh, was it in Fox News?
And Fox News, those people would, some of them would say, yes, it was faked. So the last thing they showed, they did the flag, they did the footprint, they did the bouncing thing. They did all of those things that are used as reasons to say that the government has cheated us. Took all that money that we gave for the space program and just went in the Hollywood set and made the thing, and that's what we saw on the television. That's their theory, right? So how do you prove this is wrong? It's not that easy to prove these things. And it's impossible for somebody who's deranged, and these people are deranged. But anyway, we still want to use reason on them as well, even though they don't, truck in that kind of stuff. But the reflector is a dead giveaway, you see, because any time that the moon is up and that Sea of Tranquility is pointing at us, you can go out to an observatory in California, you knock on the door and they'll let you in, and they'll do the experiment for them. They did the experiment for the Mythbusters. And the idea is they have a very powerful laser that they can point, and they can point it precisely. It really has to be, pointed precisely. The beam, by the time it gets there, is huge. It's not like these things where you don't even see the splitting, the spreading. But they have a spectrometer there that records that particular frequency, and you see the noise, and then all of a sudden, right at the 600 terahertz, not quite 600 terahertz, but close to that, up comes a peak. And they can raise the peak and lower the peak, by turning the power up and down. It's to anybody that has a rational brain, you would say, yeah, that's proof of the space mission. It actually happened. Can't get those mirrors up there, another way. So that's the thing that this particular 90 degrees has. When you put this thing right at 90 degrees, and it's hard to do from where I'm standing, I can try to match it to the coordinates there. But the deal is that no matter where you're sitting, if you're within this 90 degree angle here, your image should be showing in there, and you should be dead center. Now I'm going to come around here and try to adjust it so that it works for me, and it's pretty close right now. I didn't do too badly.
Yeah, that's fine.
That's about it right there, isn't it? So you should see yourself being reflected right at the corner. Sometimes I used to play you know how the university likes to say that they're really interested in U, right? U of A. So when I had a bunch of undergraduates in here, I said, the most important person in this class is, you will see an image of that person. Now there's an artist that's taken advantage of this with a big right angle. The thing that the artist did, though, was he coated the silvering only very intensely at the corner, and then he made less and less reflective as you worked out from the mirror until finally about this far it didn't reflect at all. The effect of that is really stunning, because it was set up in New York City where crowds everywhere, right? And so you walk by and all you see is yourself. And you know, some people are sort of on either side of you, but they're sort of fuzzy. But you have sharp image. That cool? So no matter where you are, as long as you stay within the 90 degrees of that, and it's huge, so a lot of people can see it at once, you will see yourself. Solipsism. So Ayn Rand would love it. She believes she was the only person in the universe. Okay, the mathematics of this. These are the two Pauli spinors. What do you mean two? Well, this one is the one that takes the second component and turns it to minus. Doesn't do anything to the first component. So when sigma A hits X, it gives X back again. But when it hits Y, it gives minus Y. There's a reflection. Okay? Now, if you take minus this operator, you don't need another Pauli spinor to take this mirror. Just put a minus sign on this thing and it represents this mirror. That cool? So that is something that you need to know about Pauli spinors. It's true for the B operator. The B operator is a mirror that's pointed this way. And then you want to point the mirror at some arbitrary angle. Say cosine, say you want to do it at 10 degrees or something. We take the cosine of 10 degrees for this and sine of 10 degrees for this as those operators, and you'll represent a mirror that's at 10 degrees. We don't need that little gem of effect for what we're doing, but it helps. It helps to see that. Okay, so once again, this one reflects y into x, okay, and minus x into minus y, right? The negative of that does that operation. That's the basics. Now what if you do a couple of these in sequence? If I do a sigma phi reflection, that's what this matrix represents. That's what we're talking about with the collision between the two masses is a matrix like this. Okay? Well, to figure out, what the matrix is, the best way to do it is simply say, okay, sigma phi times x, what does it do? There's a unit vector x, okay? I know that it's going to flip it up by exactly the same angle that it now subtends with the mirror. It will then have a vector here subtending the same angle, okay? So there is a vector now that has a cosine phi component here and a sine phi component there. So that takes care of the reflection that x is going to go. That's the first column of the matrix. Then you go and do the same geometry for what happens to y. Y gets sent down to here. So that's the second column of the matrix. This is the best way to, figure out matrices that are going to be group operators. This is a group operator. This forms a group. And a group is just something that when you multiply two of them, you get something else that's in the group. A group is just a set of operators that are gotten by fixing it so that every one of the operators with any other operator gives you somebody else in the group. That's the main thing. Now that by itself would make what's called a semi-group. You also demand that the group contain the unit operator, the operator that does nothing. And we certainly can do nothing here. There's no problem with that. But it also has to have the inverse of every operator in there. So anytime I do a rotation like this, I should have an inverse to it. And the inverse is really easy to get. What you do when you make, for example, a rotation is you do this operator sigma A first, say, and then do sigma phi. What do you get? Well, as you can see by just looking at the geometry, you get a rotation by twice that. The angle between the things. You have a thing here separated by angle phi. I'm sorry, separated by angle phi over 2. You will get a rotation by twice that. There's your standard rotation matrix, which is the product of this sigma A right here with the sigma phi right here. Okay? I'm going to just take a little bit of water like the candidate for president did during, you remember that guy, what's his name, Rubio? You're shaking head, you remember?
Yeah, Mark Rubio.
He was in the middle of telling everyone that Obama was such a piece of crap, and he had to stop and take a quick slug of water. He knew he was lying, his mouth was dry. But I'm telling you the truth. You reverse them, you get an inverse. Now the reflection, instead of being up, is down. So these are good diagrams to study just to get a feeling for the geometry of the reflections. And this is just in 2 dimensions. You play the same game in 3 as well, but we'll skip that because there's some extra complexity. So when I say that it's all done with mirrors, this is what underlies all symmetry analysis or group theory. I say these symmetry analysis and group theory are the same. It's just a symmetry analysis allows you to take linear combinations of all of the group operators, which is called an algebra or ring when you do that. So physicists do group theory, but they do more than that. The product of an odd number of reflections is a reflection, but an even number of reflections is a rotation. And rotations form a group by themselves. Product of rotations just gives rotations. So, you're talking about classical objects, rigid things. It's really easy to, show a rotation. We have our brains very well programmed or designed to handle, you rotating or some other object rotating. In fact, you can become a gymnast and do all sorts of, or a diver, and learn to do all of the complicated classical mechanics of rotations, and get somebody to give you a 10 for it if you're really good at it. So that is in your head. But reflections, they're a little more difficult. When was the first time that a man looked in a mirror? And I would guess that maybe the Greeks had some, but everyone had was if you have a nice pool of water and there's no wind, and optics is right, you can see your reflection, okay? And the famous myth of Narcissus is involved in that. But that apparently is not enough to evolve a brain that really can, psych out, shall we say, reflections. So you got to practice. You got to practice. And the thing that you should note, that while classical objects rotate easily, it's really hard for me to reflect this thing. See, how the hell do I do it, right? I destroy it, right? A reflection is an object, is tantamount to completely tearing it apart and then putting it together on the other side, right? But waves wave patterns are really hard to rotate. Darn near impossible. But they reflect beautifully. And that's why reflections are so important, because we're all made of waves. So at the fundamental level, you need to learn the mathematics of reflections, because that's what waves are always doing so easily. And if you can make them do it twice off of two or three, then you rotated the wave. Like these things. Okay. So, modern physics has got that in it. Now, we have here just a few minutes, since this problem isn't absolutely due by the next lecture. I'll just point out what's going on here. And what we're doing here is taking a mass ratio of 3 and looking at the Estrongian things. And it turns out this one is very periodic. This one is beautifully periodic with this ratio of 3. Now, so is the ratio of 2, which we talked about before, but 3 is interesting. And this is a picture of, first of all, the Lagrangian with the 3-to-1 ratio and in mass. And then the Estrongian is this plot right here. And basically the idea is I bounce like this, and I come right back and do it again. So this is a really simple example of that. Now, depending on where you start, if I start here, you see, I make a kind of a Star of David. If I start here, I just make this thing, which I just showed. So that's kind of a neat thing. This is the original Lagrangian picture. This is the Estrongian, where it's been symmetrized, so that it just bounces off of a circular protractor. It wouldn't hurt, I suppose, to try a few of these. This is the one that, whereas these are two very special cases. This is the 1-0 case. This is the 1-1 Super Ball case. And if you want to go ahead and set her up for 6-to-1, or 0.6 to 0.1, I suppose. Just do 6-to-1. You got to be careful with square roots of 10 is not a nice number for what we're doing here. So you'd have to multiply by 100 to make it small. I think you can just do it
6-to-1 mass?
Yeah, just do 6-to-1.
Okay.
And it ought to, not get in its hair.
Boost the scaling.
This is one where you can probably speed her up a little bit without having any problems. By the way, I should ask you a question, is if you change the number digitally by typing, does it take it? Yeah, see, there it stopped.
It finds him.
Yeah. So you're seeing over there in the V plot, it's a little hard for me to see because I'm at an angle, but that looks like this plot right here. Yeah, it is, because you had a 0 on M2 to start with. So this is a Poincare recurring system, very obviously. Now, if you started off with 1 and -1, you get a different looking pattern, but it still has the symmetry, as it were, of this object.
That's a 1 and -1 there.
And then what I'd ask you to do is something like 2, or 1.5, and 1 after this one finishes. So that's this one right here. And it has to go a little bit more See, it's now come back to the right, but it's not where it was before.
What's this a little bit speed-wise?
Yeah, live dangerously, let her bang, yeah. There you see what's going on. Now it's going to recur. You see, it took it several run-throughs, back and forth, let's say, before it settles down and should always be on those highways. It's cut the highways and then it just travels on. So that's a little different from a Poincare recurrence where, you know, you would just make a figure on one pass and always do it the same way. This one has some multiplicity. This one, same system, but now do a 1.5 and 1 or something like that.
And then velocities?
Yeah.
0.5? Or just 1?
Yeah, let's see. The idea is that you're going to get a fairly complicated collection now.
Now it's
Right?
filling the space pretty well.
Yep. Almost looks like it's going to go ergodic. Now what's so interesting about systems like this is that in the parameter space, there's presumably an infinite continuous set of ergodic cases. But there's so many of the rational cases hiding in there that it can they almost look like they're everywhere. And this is what happened to Ulam and Ulam and Fermi and a bunch of others with Los Alamos. They had this computer so they could do stuff like this. And of course, the computer was the only one in the world, so they said, what can we do? Well, let's prove that statistical mechanics axioms are correct, that let's put in a typical potential, and we'll let the thing see if it thermodynamically equilibrates and goes ergodic. You know, we want to show that. It didn't, and then it didn't, and then it didn't. They thought there was something wrong with the computer, but it wasn't. The particular Hamiltonian, which was easy to program, had symmetry, and it wouldn't go ergodic. It would make patterns. This really freaked them out. And you can read more about this in the Los Alamos magazine that talks about the life of Stanislaw Ulam, who was a very creative character. Anyway, the reason I bring all of this up is because these operators, and this is now being very careful with the notation of them, that is thinking of some starting state, and TC was just showing you several examples of where I could pick a starting state that would, you know, give me a full set, you know, full look at the symmetry, paths that were as ergodic as is possible. Whereas if I pick the initial state to be on a reflection plane somewhere here or there, I may not get them all. So the idea is, do all the group operators get to act? That really depends. Here is a typical non-trivial reflection through 30 degrees, okay? Consists of cosine times the sigma A operator, and then sine times the sigma B operator that are up here. A for asymmetric and B for balanced. Those are the Pauli operators Z and X in the normal notation of a typical quantum mechanics text. But here we're just looking at a typical example of a Pauli spinner at 30 degrees. And that's kind of neat. And the idea is that after you've done a 30 degrees, you can multiply that thing by an operator that does a reflection sigma Z, and you know, see what you get. And then do it again and again until finally, and I'll skip to that right now, there's the floor bang that can be included in there as well as the ceiling bang. And the idea is to look at the whole set of possibilities. I reflect this one into that one, okay? I use this reflection to reflect this one into that one. There's a sigma 30 that gets it, you see? I want you to get used to using group operators, first as taxicabs that take you places, but then as actual coordinates that name a state, you see. This is the state R60 if I call this home base, the initial state. So once I've done that, then it's really easy to do multiplications. For example, find the product of sigma 30 and sigma minus 60. What is it? Well, first you find the sigma 30 plane and the state sigma minus 60. And you see that what you need to do is look at the reflection sigma 30 of that one will be some other element in this group. This is how you multiply the groups, okay? And if you do that operator, sigma 30 on sigma minus 60, we have to first of all find sigma minus 60. Sigma minus 60, this guy right here is in blue. There is sigma 60, and there is sigma minus 60 down there, okay? So if I do this reflection, sigma 30, okay, there's its plane, there's this mirror plane right there. I know darn well that I'm going to take old minus 60 here and drive it through the mirror to that one. And the name of that one is I, for inversion or completely flipped. So the answer to that particular product is that. So you can sit here just with your eyeball and write the group table down, you see. That's group theory, as mathematicians would call it, multiplying group operators. Now the physicist group theory is finding matrices that represent these. We've already done that, so that's also a beginning of the physics group theory. But the thing that I find most important is that you want to label all of the possible physical states in a symmetric system with operators. Once you've done that, finding eigenvalues and eigenvectors is really easy because the group knows already its algebra. So it can solve all of the polynomial equations that are possible using that set of algebraic elements, including secular equations and spectral decompositions, all that kind of stuff. This is just a start on that particular avenue of research and techniques. All right, I think we've exhausted our time plus 5 minutes here, or more. But if we haven't burned out the memory or the battery, we've got a tape of this particular lecture. And I thank you for your patience.